Okay, so now we're going to talk about long straight current and permeability. So let's say that we have a magnetic field that's being generated by a wire that's carrying a current, okay? So remember that I, the capital I, stands for the variable current. And this little dot here means that the current vector is pointing towards us, all right? So the current distance vector is pointing straight up towards you. So that means that if we want to figure out what the magnetic field is going to be because of that current, and remember, whenever electrons move, a magnetic field is generated. So if we want to find the direction of the magnetic field, we need to use the curved finger right-hand rule. And to find the direction of the magnetic force, it's the straight finger right-hand rule. So this one, we're going to use the curved finger right-hand rule. So we're going to point our thumb in the direction of the current, okay, which in this case it's coming out, and then our curved fingers are going to move in the direction of the magnetic field. So in this case, our fingers are curving counterclockwise, and so that's what our magnetic field is going to be, is counterclockwise loop. Now, as you move further and further out away from the current, the magnetic field that you're generating is going to get weaker and weaker, right? But it's going to be spread out over a larger surface area or a bigger circle with each successive increase in distance away from the wire, okay? So because of that, that means that the magnetic field strength is going to be directly proportional to the current in the wire, okay? So more current means that you're going to have a stronger magnetic field strength, okay? It also means, because we're increasing this circle each time and you're getting further and further away from the current, that means that the magnetic field is going to go down. So that means that the magnetic field strength is inversely proportional to the circumference of the circle. So now we can combine both of these proportion statements here. We can say the magnetic field strength is proportional to the current over the circumference. Now I'm going to change to the formula for circumference, that 2 pi r, and 2 and pi are constants, so we can get rid of those. That means the magnetic field strength is proportional to the current divided by the radius. Well, if we want to turn a proportion statement into an actual equation, then we need to multiply by some sort of a constant, okay? Now, our constant in this case is going to be the permeability of free space, this mu naught right here, okay? So mu naught times I, the current, over 2 pi r, the circumference, okay? Now r, that's going to be the distance to the long straight current. So in this case up here, remember the current is coming through the center of these circles, and so r would be the radius out to either of these circles, either of these distances away from the wire. The permeability of free space, we're going to use the permeability of free space in a vacuum. And I've given you this value before, and it's on the AP formula sheet, but here it is again. So it's going to be 4 pi times 10 to the negative 7th, then Tesla meters over amperes, okay? So you don't need to memorize this again because it's on that formula chart, okay? Now, what is the permeability of free space, or the permeability at all? That is the ability to magnetize a material, okay? So for ferromagnetic materials like iron and cobalt and nickel, and some other alloys, they can have like a pretty large permeability of free space, okay? Other materials, not so much, like rubbers and plastics and stuff, they would not have a very good or a very large permeability, okay? This is why when we make electromagnets, maybe you made one in middle school or something like that, but you always wrap a coil of wires around an iron core. So usually they have you wrap it around like a nail or something like that. That's because these ferromagnetic materials like iron can have a very large permeability of free space. That means that this number right here would increase. And so if this number gets bigger, then that means that this number here is multiplied by that factor, by whatever it is. So you can actually increase the magnetic field strength by increasing this permeability number. And so if you use a ferromagnetic material, you can do that. So that's why these wires are often wrapped around some sort of an iron core, so that you can increase that magnetic field strength rather than just having a solenoid coil here with no core inside. All right, let's work a practice question. So two long straight wires are perpendicular to the page. The current in one wire is 20 amperes into the page. The current in the other wire is I2. The net magnetic field is 0 and point P between the two wires. Or point P is at a point between the two wires. Find the magnitude and direction of I2. Okay, so if we have I1 and this X right here means that I1 is going into the page, okay? We know that one of the things that we're going to have to figure out is which direction is I2 pointing, all right? And we know that at point P right here, we want the magnetic field strength to be 0. So we want these things to cancel each other out, all right? And we know that this point P is 0.05 meters away from I2, and that it is 0.1 meters away from I1. Okay, so we know if we want that magnetic field strength to cancel out, then we're going to have to set the magnetic field generated by I1 to be equal and opposite to the magnetic field generated by I2. And since these magnetic fields are being generated by a long straight wire, then we'll want to use our new formula for magnetic field strength that comes from a long straight wire. Okay, so that gets us to this point right here. So we're going to say that current 1 generates magnetic field 1, and current 2 generates magnetic field 2, and that they need to be equal to each other so that they'll cancel out and give us 0 magnetic field strength here, 0 Tesla. All right, so we have our new equation, and we're putting subscripts of 1 in here. And then we have the same equation with subscripts 2 here. Now, the wires are the same. They're made of the same material, so that means that the permeability is constant, so that can go away. 2 and pi are constant in both sides, so that can go away. And that leaves us with I1 over R1 equals I2 over R2. Okay, so then we can just plug in the information that we were given in the problem up here, and we want to solve for I2. What's the strength of this current when the wire is located at this position away from P such that it gives us 0 Tesla magnetic field strength? All right, so we can plug all that in and say, okay, well, you need 10 amps to be running through that wire in order to make that true. But now we need to figure out what direction should the current flow be in, okay? Now, obviously, it has to be perpendicular to this plane of the page right here. So we know that it's going to have to either go into the page or come out of the page, okay? So we need to use the curved finger right-hand rule to do this, all right? So over here, since the current is pointing into the page, we're going to point our right hand thumb down into the page, and that means that our curved fingers are going to curve clockwise like this. that means that at this point P right here, we're going to have the magnetic field lines come around and be pointing down like this. Okay, so I1 is in the center over here, and this is where point P is. Okay, so the magnetic field lines are pointing down. That means that we want the magnetic field lines caused by I2 over here that lines up with this wire. We want these magnetic field lines to be pointing up so that it's equal and opposite. Okay. I2 is kind of out of place. It's not going to be in center, so I'm going to move that. Okay, so we want these magnetic field lines to be pointing upward. So let's see how we could make that work. If we were to point our thumb up out of the page, there's no way that I could twist that's going to make the magnetic field lines be pointing up over here. So let's keep my thumb pointing down into the page, and look there. My curved fingers match what I've drawn on the page, okay? There would be a point where they would curve around and be pointing up at point P. That would cancel out the magnetic field lines generated by I1. Okay, so that means that when I do that, my thumb's pointing down into the page. That means that I2 needs to have a direction into the page. And so that's what we have down here, that I2 is into the page. So a complete answer for what's the magnitude and direction of I2, it would be 10 amps into the page. Hopefully you found that helpful, and I'll see you in the next one. Bye.